in this lecture, we would like to explain what optimization problems are. In particular, we will focus on discrete optimization. So the difference between continuous and discrete is that in discrete optimization, your variables can only take some discrete set of values instead of a real number in which you have infinitely many possible values of variable, right? So the idea of an optimization problem usually is the following. So we want to minimize a function, okay, of some multi-dimensional variable. So x, we can think of x as a vector with some first component, a second component, etc. And n components if you want. Okay. If the problem is discrete, this x component, the x1, x2 components of x take values within a discrete set. Okay, let's go in a finite set. So the goal of the problem is to find the argument of this function which minimizes its value. So the goal of the problem is just finding if this S is the set of all possible x's, so find which x is the one that minimizes this cost function. So people also formulate the problem as a maximization. Okay, this depends just putting a minus sign in front of the cost function to change the problem from a minimization or a maximization. Okay, now in this course we'll just take the convention that our goal is to minimize this function. Of course, there are infinitely many possible functions. The question is how we address this problem. And then there is the restricted family of problems that is the QUBO, which stands for quadratic unconstrained. A binary optimization. So a QUBO problem is a specific shape of this cost function in which the cost function can be written as follows. Some matrix Q. And this, okay, here this is a convention of what we call a vector column or a vector row. Okay? Some people usually put the transpose here, but okay, this doesn't matter. The key question here is that this vector x in a QUBO problem, so the components of this vector, let's say xk, can take only two values, so either 0 or 1. So it's a binary, x is a binary string. If you want, we can write this as x is just an element of the power set 0, 1. Okay. So we say quadratic is because in the cost function we have quadratic expressions. It's a polynomial of degree 2. It's a constraint because notice that there is no constraint on which conditions these bit strings need to fulfill. It's binary because the elements of the components of x are basically bits, and optimization because the goal is finding which element x, which bit string minimizes this quantity. So this problem, at the first sight, it can look like very specific. Okay? So in the rest of the lecture, I would like to show you that these QUBO problems are very general, and that in many cases, when I have a cost function that has no shape, if I am smart enough, I can transform it into a QUBO problem. So basically, what I will try to do now is to relax the condition of being binary. So we'll show that we can map a problem into QUBO even if its variables are not bits but are integers, for instance. I will relax the condition of being constrained because we'll see that having a purpose function where we want the possible solutions to fulfill some conditions, we can impose that also with a QUBO. Basically, the idea of being quadratic. I will show as well that even if a cost function is not quadratic, with some smart techniques, we can also map it into quadratic. Okay? The idea of the objective of this lecture is to show that the QUBO problems are a very general family of problems, that many interesting problems can be mapped into them. And this is what precisely we'll do in the next lecture, mapping practical problems into a QUBO formulation. Okay, so let's start by relaxing the binary condition. So what do we do if we have a problem, a discrete optimization problem, in which the variables are not bits but integers? So let's answer this question. Okay, so what I would like to show now is that if we have a quadratic problem and constraint, but with variables that are integer instead of binary, so the component, the kth component of the z vector is no longer a bit, but it's an integer, so that it takes some value in a range, okay, where zk can take different values. Of course, that these different values are somehow arbitrary, so we could shift with a loss of generality the interval of these integers. Okay, but if z can take an integer value, we can also write this optimization problem as a QUBO. Okay, the way to do it is very intuitive. The only one thing that we have to do is that we can represent an integer number with a bit string, and then in this way we will be able to write the problem, the QUBO, the optimization problem, into a problem of optimization of bit strings. The only one thing that we need to do is to write the component zk as a bit string. So an integer can be always written as in binary representation. So basically, what we do is the following, where n is the length of the bit string, and okay, so this I is the I bit of the block k, and so basically we should understand this as follows. We have some z that is a string of integers, right? So we have z1, z2, etc. Right? And now this z1, so basically this z1 is written as a bit string, so it will have these components, etc. up to n-1. And the same will be done with z2 and etc. So basically, what we have made is that we have changed a string of integer elements of z by a bit string whose length is n times larger. Okay? So by taking this price, we are able to transform this cost function, that was a cost function depending on integer values, on another cost function that is also quadratic, that depends on binary values. Okay, so in this sense, we see that by increasing the amount of variables, we can encode any integer problem into any integer problem in which there is a maximum value. Of course, the set needs to be finite. Okay, but any optimization problem quadratic, when we use integers, can be mapped into QUBO with binary variables. Okay. The next step, it will be relaxing the condition corresponding to the shape of the function. So what I will show now is that also functions that are not quadratic can also be mapped into a QUBO problems. Okay, so the next condition that I would like to relax is showing that even problems that, so cost functions that are not quadratic can be transformed into a quadratic one. So let's see an example. So one trivial example is the case in which, okay, we don't have a quadratic function, but we have a linear function. I don't know, let's, for instance, imagine that in our cost function, we have an expression like this one, okay? Turning this into quadratic is very simple, because notice that x1, in this case the variable x1, only takes the values 0 or 1. Therefore, x1 is the same of x1 squared. And with this simple strategy, we just transform this one expression that would be 3x1 squared, and okay, we will be done. Okay. Of course, the complicated part is having expressions that are not linear and not quadratic. So, for instance, I don't know, imagine we have some expression like 14 x1 times x3 times x7. Okay, this this is a term of order 3, and we would like to transform this into some terms of lower order, of order 2. So the only one strategy that we have is just so it's divided into fours. So the first step is merging variables into a new variable. So if I do this, for instance, I create a new variable, y1. I put it the level y just to make it different from the variables x. In practice, of course, this will be, if I don't know, in this problem I had 7, so the x had length 7, so this would be x8, for instance. Okay, but now clearly with this condition, this transforms into a binary condition that is this one here. So into a quadratic expression that is one here, right? So we are fine, but the question is, we have somehow to impose, we have to add something that imposes that this variable y1 is indeed equal to x1 times x3. Okay, this would be adding a constraint. That is the condition that we will relax afterwards. But there is a nice result where we can see how this can be imposed. And for this, I need to call result from Rosenberg. Okay, so I would like to convince you that if I add this penalty term with the Rosenberg penalty term that I have written here, then this implies that if this thing is minimum, then I can guarantee that the new variable y1 will be equal to x1 times x3. And to see this, let's do a table where I write the following values. So I have x1, I have x3, I have y1, and the penalty term, right? So what I would like to convince you is that indeed, if y1 is equal to x1 times x3, this penalty term is 0, and if not, if this condition is violated, then the penalty term takes a positive value, such that when we perform the minimization, because we want to have the new possible value of the cost function, this will guarantee that indeed the bits x1 times x3 will be the same as y1. And in this way, we we will have been able to decrease the order of our polynomial from a polynomial of degree 3 to a polynomial of degree 2. Okay, so let's see. Imagine that x1 is 0, x3 is 0, and then we want y1 is 0. Then notice that if I evaluate this penalty term, indeed everything is 0 here, okay, and indeed the penalty term is 0. Okay, if x1 takes the value 0, x3 takes the value 1, and y1 takes the value 0, which fulfills this condition here, right? Then the penalty term with the calculation, right? And everything is 0 except to x3. We notice that this penalty term takes the value 0. So if instead, the variable y1 takes the value 1, while x1 is 0 and x3 is 1, clearly violating this condition, we notice that then the penalty term is no longer 0 and takes some positive value. In this case, we would have that this minus 2 plus this 3 with the contribution of 1, okay, which is positive. And therefore, this configuration will be forbidden in the solution. Okay, so we could check all the possible values for x1, x3, and y1, and we would see that adding this penalty term to the function, which is a quadratic penalty term, okay, so this is r, okay, so in our cost function, we add, we just plug these two variables in one, and then we add this penalty term, the Rosenberg penalty term, then we are able to reduce the degree of the polynomial. Okay, so with this you show that a cost function that is not quadratic, it can also be reduced to a quadratic cost function. Take the cost of adding more variables into the cost function. Okay, basically every time that we want to reduce by 1 the degree of the polynomial, we need to add an extra variable. Okay, but with this, we relax the second condition of QUBO. So, okay, now, last but not least, we will show how to rewrite a problem that contains constraints such that it can be written without constraints. Okay, for this, it's important to distinguish between two types of constraints. Constraints that are strict, I don't know, for instance, okay, we have some function, some variables x, and we can, one way of imposing the constraint, right, is that we're writing that this function of x needs to be equal to 0. No? This is a constraint. Imposes that not all the x are valid, but only those that fulfill this condition. Okay, so basically the way to impose, we have a cost function where we want that this minimization, right, is not made over all the strings of length n, but in the strings that fulfill a condition that are all the strings that such that the f of x is equal to 0, right? We would like to impose this condition. So one way of doing this is simply performing the minimization over all the strings of length n. And now we add a penalty term. We add a penalty term that we make this function square in order to be sure that it's positive. And here we can add a coupling, which is called Lagrange multiplier. Okay, so the role of this coefficient here is to make the constraint stronger or weaker. Okay. If the constraint is, if this coefficient is too small, it could very well be that we find solutions that violate it because they are very good. They are solutions that are not physical, so that are not valid, but because the cost function is so, the solutions have a cost function that is so smaller than the ones that respect the constraint, and we could obtain solutions that are not valid. In contrast, if this Lagrange multiplier is too large, then usually what happens is that you always fulfill the constraint, but the optimizer doesn't find the accuracy to distinguish properly between different solutions, because the energy scale is given by this Lagrange multiplier, and the cost function really doesn't discriminate between different solutions. So it's a kind of an art finding a value of the Lagrange multiplier that provides you solutions that are realistic or that are practical in the sense that they fulfill the constraint, and at the same time that are good because they have a good value for the cost function. Okay? Said that, this is the way in which we impose constraints that are, let's say, rigid constraints, right? Okay, so let us also mention that the constraints that we can impose don't have to be necessarily strict constraints, so with an equality, but we could also impose constraints that are expressed in terms of an inequality. For instance, we could suppose that we want that our solutions also fulfill the condition that are negative or zero. Okay, this type of constraints can also be imposed, and the way that we use to impose them is adding an extra variable. So we can see that if this quantity is negative, this can be well expressed in this way. We add an extra variable that we will add to the QUBO, and we can express this as an equality constraint, given that this variable is positive, like most of the QUBO variables are. So okay, so basically we could just add this constraint by adding a new lambda coefficient or a new Lagrange multiplier, such that this is the case. And so we have seen that basically also constraint situations, constraint problems. So problems in which our space of solutions, we don't consider them all, but just the ones that fulfill some particular constraints can be also mapped into a QUBO formulation at the cost of adding extra terms here. And the art in this situation is choosing properly this Lagrange multiplier. So basically, what we see so far is that even if our problem is not binary but integer, even if our cost function is not quadratic but polynomial, and even if our problem is not unconstrained, we want to constrain that type of solution, in all these cases, there are techniques that basically consist of adding real variables that allow us to map the problem into a QUBO formulation. And that's why we will focus in this course on the QUBO problem. One last thing that we would like to mention about the QUBO problems is that they can be put in correspondence with the classical Ising model. So this is the Hamiltonian of the Ising model, and as you can see, this is a quadratic Hamiltonian. The key point here is just to understand that while the QUBO problem is formulated in terms of binary strings, so this we had this X composed of elements that were bits. These spin variables, they are they are also binary, but they don't take the values 0 and 1, but the values -1 and +1. So we need to just perform an easy transformation that maps the binary variable xi that takes value 0 or 1 with a speed variable sigma I that takes values -1 or +1. Okay, and the transformation that does this is simply just a linear transformation where we basically notice, right, that we could do, for instance, x I is just 1 minus sigma I over 2, such that when sigma I takes the value 1, xy will be 0, and when sigma I takes the value -1, this is 2 over 2 is 1. Okay, so in this way, we just map the two ways of incorporating these variables and applying this transformation into the Ising Hamiltonian. Okay, in this case, we can go from the Ising Hamiltonian to the QUBO problem, but we could do the operation in the other way around, so it doesn't matter. So we see that from this equation, sigma I is equal to 1 minus 2 xi, and if we substitute these variables in here and arrange things, we will notice that we will be able to write it as a QUBO problem. We just have to derive which are this matrix element depending on J, E, H, I. Okay, so with this, we believe that we have motivated enough why QUBO problems are interesting. And this last connection with this model will be very interesting when we try to solve the QUBO problem by means of annealing techniques, both simultaneous annealing and the quantum annealing that we'll see later in this course.